Okay, so let's look at these formulas, solids computation, all right, sludge computation formulas. The first one is the volume, all right, and you know this very well. This comes from the definition of specific gravity, right? Specific gravity from this one, right? Specific gravity of anything. In this case, it's of the solids, right? By the way, these residuals, all right, especially in both of them, especially in the wastewater treatment plant, most of it is water, by the way, in the sludge, right? So here we are talking about solids inside the sludge, which means a small fraction of the sludge. The rest of it is water, right? Well, it's dirty water, but it's water. So specific gravity is the density of the solids, or whatever is that thing. It might be the sludge, it might be the solids, divided by rho of water. We know that from this definition. So this can actually is volume of the solids equals mass of the solids or sludge, whatever is that thing, divided by rho of the solids divided by rho of water multiplied by rho of water. This is water here, by the way, right? Water. And you understand that this cancels this, right? Now, what is this? Look, this is nothing but ms, which is the mass, times volume, rho of the solids. And here you understand that rho of the solids, rho, what's the definition of density, guys?
Mass over volume.
Thank you very much. That's actually mass over volume. And here you understand that this cancel as, and you get ms equals ms. So this is from where they got this formula, from through two definitions, the definition of rho and the definition of the specific gravity. That's it, very simple. All right, now, this is can be applied to anything. If you are not interested in solids, but in the volume of the sludge, SL, sludge, then it's gonna be the same story. All right, M of the sludge, all right, divided by the specific gravity of the sludge times rho of water. Okay, so simple formula that enables us calculate volumes. Actually, this is what eventually you want to calculate volumes, right? You need to figure out how much you're going to produce of whatever you are looking for, sludge or solids in the sludge or maybe water itself. Okay. Now, sludge, as we said, is solid and water. All right. If you want to write it in terms of mass, here it is. If you want to write it in terms of volumes, here it is. Now, if you bring the volumes and write it from the form that we just saw in this video, sorry, not video, in this slide, instead of write it volume, you can take this side and put them together here. All right. You can use this formula as well. No question about it. Okay. Very simple. Always remember, sludge is solids in the sludge plus the water. You want it in mass, here in mass. You want it in volume, here in volume. You want it with the specific gravity, here it is with the specific gravity. As I said, it's a buffet. You choose the formula that you need. All right. Another form of formulas, sometimes we write it as a percent. as a fraction, all right? So if you're looking at the percentage or the fraction of solids, it's gonna be the mass of the solids divided by the total mass. And we agree the total mass is nothing but the solid plus water. Or you might be interested in the fraction of water. Well, it's the same, but you're gonna find the mass of water divided by the total again. All right, so this is another, or these another two sets. Right? Now you put them back in that formula and do some kind of massage here. We are not going to do that, but you get this formula that is also needed. It is the specific gravity of the sludge, right? So you have a formula for volumes. Now you have sludge. Be careful if you want to figure out what's the specific gravity of the sludge. You need to figure out what the specific gravity of the solid, percent of the solid, and percent of water in this formula. All right. Well, this is actually, this one came from here, but this is one. Sorry, not this one, here. Specific gravity of water is equal to 1. Well, raw water divided by raw water is 1, right? So this might be needed formula a lot. And the volume of the sludge is also needed formula a lot, right? Good. So two formulas here, one for the specific gravity of the sludge, and the other one is the volume of the sludge produced. Now, the mass of the solids, all right, or sometimes you can call it dry sludge, dry, solid, no water in it, solid. It depends what you are producing and how much you're producing of it. All right. This formula is when you add alum, see this is A, it is the alum dose. Remember alum dose, when you add alum and you stir it, and all these turbidity, right, impurities gonna aggregate and precipitate. That's solid stuff. And you understand that the amount of that solid depends on how much is the dose of the alum. All right, alum dose. Q is the flow rate, meter cube per second. SS is the spended solid in raw water. And M if you have other kind of chemicals. F, not no. If you are not using alum, you use another one. So instead of this, gonna be that one, all right? But be careful, the numbers here are gonna be different, right? So this formula is good only for alum. You have another thing, you will have that formula for it. These formulas actually are available everywhere. Right? If you need it in the exam or somewhere, it's gonna be given to you. Right? Gonna be given to you. So that's for alum. You have another one if you choose to use iron, right? Fe. Yeah, it's gonna be different numbers, not 0.44. Gonna be 2.9. Anyway, this formula gives you the ability to calculate the mass of the solids produced based on whatever you are doing. Okay. Fixed inorganic and volatile organic fractions can be calculated through these formulas as well. All right. Specific gravity of solids can be calculated through this one as well. All right. So these are sets of formulas for calculating or computing different things. You choose the one that you are interested in. Very simple, very easy to follow. All right. Let's look at this example if you don't have questions. No? All right, let's look at this question. Look, there is a treatment plant here. They are adding coagulant. The flow rate is 0.5 meters per second. This is your what?
Is your Q.
That's your Q, thank you. So Q equals 0.5 meter cube per second. Doses with alum, what's that?
That's
The
your
dose-
A.
That's your A, thank you, in that formula, right? Looks like we're using alum, and we need 23 milligrams per liter. This is the dose of alum A. No other chemicals are added. Let me go back here. What is it? Here. Other chemical added. This is your M. In our example, M equals what? How much?
M would be 0, right?
Yep, thank you. They are telling you just straightforward. No chemicals are added. So M equals 0. The raw water suspended solid concentration is 37 milligrams per liter. Suspended solid concentration. Let's go here. Is that what we are talking about?
Yep.
Yep. So let's write it down. SS 37 milligrams per liter. Okay. The effluent suspended solid concentration is 12. The effluent, all right? 12. What's that? The effluent suspended solid is 12. Sorry. Here. The effluent suspended solid concentration. Looks like fraction, right? Suspended solid fractions. Remember that? Suspended solid fractions. Is that a concentration, guys, here? Effluent. Concentration of effluent. Let me write it this way. Effluent concentration. Suspended solids, right? Equals how much? 12 grams,
Milligrams per.
right? Okay. The sludge solid content is 1% fraction, looks like, right? Can we write this as PS equals 1%?
Yeah.
The specific gravity of the sludge solid only, right, is 1.2. So is this SS? Yeah.
That's
So I guess I'll let you
the
take care
SF,
of all of the things for real.
SF or SV.
I don't know how you pronounce your name, but
No, the solid. It's not the sludge. If the sludge, you wouldn't have this word, I guess. Right? For me, it looks like SS, not SSL. Right? Or you are talking about something else?
Yeah, it's SF. You're right.
Yeah. Well, let's see. Let's see anyway. Let's go there and see. They want you to find the volume of the sludge. In other words, they want to find what? Sludge, see the sludge, not the sludge solids. VSL equals what? All right, so let's go back. What formula are we going to choose from this buffet? Is this the one that might help us? The volume of the sludge, here it is. All right, so this is a formula that we are going to use. But before that, let's calculate the mass of the solids using this formula. All right, let's put the numbers here, maybe easier, and make the calculations, find MS. That's the mass of solids produced in that coagulation basin, all right, because we added alum. So this is going to be your, how much is a Q?
0.5.
0.5.
Okay, so here you need 0.5. How much is A?
23.
23, that's correct. This is 23. SS,
37.
37. M,
0.
0. Okay. Look, are your units okay? Milligram per liter, meter cube per second. Okay, guys, your calculator, please.
I got 2035.58.
Okay, so that's 2035.
Yes.
Yes, second.
How much you said?
I
And that's
second
gonna
that. That's what.
58.58.
158. Okay, that's fine. You can just. Okay, this is kilogram per day, right? All right, let's take this number there. Right. We'll come back here to the other formula. Leave it. All right, so our MS is calculated now. In other words, this is what comes in. So it looks like your treatment, right? This is gonna come to the clarifier N, right? And something gonna be removed in the effluent. All right, in the effluent. So let's calculate what is removed in the effluent, right? This is what's gonna accumulate here. Make sense? This is N, right? Sludge produced each day. You have some of them in the effluent here. It states that clearly. The effluent suspended solids concentration is 12 milligrams per liter, right? So it's not all that comes in gonna be, right, leaving. Some of it gonna accumulate here, some of it gonna be leaving, right? Remember, if you have a concentration and Q, you have here concentration and Q. All right. From the mass balance, if you still remember from the mass balance, right? The rate, mass rate. Can we calculate the mass rate? M divided by T, I guess. Through CQ, remember that CQ? Concentration times flow rate. Concentration is a mass divided by volume. And this is volume divided by time. Volume cancels the volume and you get mass over time, right? Well, we just got the answer, kilograms per day mass per time. So here we can use CQ that we know from mass balance. So let's put this here, all right? That's gonna be mass rate of the solids in the effluent. Let me write here, effluent. And it's gonna equal C, here is C, 12 milligram per liter. Be careful now with these units, times Q 0.5 meter cube per second. All right. Now, to be consistent, the answer should be in kilogram per day, right? Because what we have just calculated was in kilogram per day. So this must be in kilogram per day. All right. Let's see how to convert that. This is milligram, you need kilograms. So what you're gonna do here? Multiply by what?
10 to
10
the
to
6.
the 6.
Okay, milligram to gram, 1,000, right?
Yeah.
And gram to kilogram, another 1,000. Make sense?
And it could be
Yeah.
dark.
So are we dividing by a million or multiplying by a million? From smaller to larger.
Dividing.
We're dividing, right?
Yeah,
Dividing.
That's correct. Okay, that's good. Oh, again, from liters to meter cube.
It's
What you are
1,000,
going to
right?
do here? Huh?
I think you multiply by 1,000. Wait, 1 cubic meter is 1,000 liters.
Yes, 1 meter cube is 1,000 liters. So you are multiplying by a, right? Multiply 10 to the third. And what else we need? Second day. What you are going to do with that, guys?
86,400.
Multiply or divide?
Multiply.
8,6,400, right?
Yeah.
Okay, let me see how much you get, guys, here, if this is correct or not. This is something wrong with these numbers. Oh. Milligrams per liter, I think, is the same as a gram meter cube. Oh, I think you're right. Yeah. Okay, try this. Give me an answer, please. Let me see.
Getting 518.4 kilograms per day.
Okay, so the answer here is 518.4, you said?
Yeah.
Kilograms per day, right?
Yep.
Okay, that's good. That's good. That's good. Thank you. Who got the same answer?
I got the same.
All right.
That's
That's
the same as well.
Yeah, me too.
so in the effluent here, you have 518. Let's remove 0.4, guys. And in the influent, remember that number? What? 2,038 or 35?
3.5.
All right. So 35 is produced. However, all right, 518 gonna be carried with the effluent. You cannot do anything about it. Now you need to figure out how much accumulates here. So here gonna be that mass balance, guys. 0.35 minus 518. How much is this?
518.
518? No.
15, 17?
Yeah, 15, 17.
Okay, 15, 17, that's good. So you have 15, 17. Now be careful. This is kilogram per day, right? This is how much you got solids, right? Let's remember this number. Okay, what you are going to do now? We need to calculate VSL. This is the goal. So let me go back here, VSL. Here, this is what you are going to calculate, all right? What we know. This number is known now. Let me just remove these circles. Oops. All right, that's fine. This number is known now. This is how much accumulates. This is your 15, 17. All right. This row is row of water. Is that correct, guys? This is 1,000. You still don't know this. All right. Now, this is what? This is the percent solids. Do we have that number
Yeah,
given in the
1%.
question?
I think it's 1%, right?
That's 1%. Thank you. Here it is, percent. So let's take that there. So this is 1%, which is 0.01. All right. So we cannot do anything unless we find the specific gravity of the sludge. All right, where is it? Should be some kind of formula here. All right. So the formula is here. Let's put the numbers here then. Here it is. Is this given SS?
Yeah, it's given.
1.2.
SS is 1.2. Here it is. All right. So this is 1.2. PS, percent solids, guys,
0.01.
0.01. We just wrote that. Plus SS is the same, 1.2. Now be careful with this one. What's the percent water?
0.99.
Thank you. Thank you. If that is 1%, the remaining water is 99%. So this is 0.99. All right, guys, give me a number.
I'm getting 1.0017.
Okay. Is that enough one? Whatever.
One's good.
Yeah, well, it is just you see what's going on here? What's the specific gravity of water?
1.
What's the
One.
specific gravity of your suspended solid sludge?
Ooh,
1 per
1.
1.2.
Yeah,
1.
1.
Okay, let's write 2 here. See what's the difference? It's actually the sludge, mainly water. And this is why you see that the specific gravity of the sludge is almost 1. Well, a little bit more than 1, right? Well, because it has some solids in it, but it's very close. All right. Okay, let's take this number then back to the formula that we started with to calculate the volume of the suspended solid. Here it goes. Here, this is 1.002. 2 zeros or 1 0? 2 zeros. All right, now go ahead and give me some number for the volume.
I got 100.
151.5.
Yeah.
All right, 151, that's good enough. That's what? Volume,
meter
Cube.
cubes per day.
that's meter cube per day. So this is how much your daily production of the sludge in that water treatment just from the alum, guys. All right? That's just from adding the alum alone. You need to deal with this, right? Okay, so it looks like here. Again, it is just about what formula to use. Be careful with units, another thing to look at. Yeah, here it is. That's correct. 150. Okay. Any questions? All right. Let's look at quickly now types of sludge, either primary, because it comes from the primary treatment or primary clarifier, or secondary, it comes from the secondary clarifier, or tertiary, it comes from the tertiary treatment. All right. The difference between them is what is the content, all right? What's there in it? In the primary, you might have nitrogen, phosphorus, solids, but mainly organic material, all right, from the primary. Remember we said in the primary, there is a certain amount of BOD removed, but not all of it. So here it is, organic still some of it, but some of it is removed. From the secondary, organic material, all right, from the secondary. However, here you have bio, all right, biosolids. That's because you have, especially in wasted biosolids. That's bacteria, in other words, all right? You will see down the road, this is one of the goals to get rid of that bacteria, microorganisms, all right? It's not only get rid of these solids, all right, dirt. You also need to get rid of the microorganisms. All right. Tertiary, also it depends what you use for tertiary, but mainly you're gonna have phosphates, all right, phosphorus compounds. Okay. So these are the things that we have to manage as solids in the sludge. All right. Now, the goal actually is very simple. You need to reduce the volume, all right? Why you need to reduce the volume? Because it's going to be costly for you if you don't do that, all right? So this is the cost reduction, right? Because the disposal costs are high, so you need to reduce the weight. And the best way to reduce the weight is to get rid of water, as we just said. Sludge, mainly water. So if you can get from water, you're going to reduce a lot the volume and the weight of the sludge, all right, in this case, and you're going to pay less money, all right? And plus, you're going to make sure that you get rid of microorganisms because many of them might be pathogens, right? Carrying some kind of disease-causing bacteria, all right? So water removal is the goal here, and pathogen destruction, all right? There are many methods to do that. Depends what is the volume produced, all right, and what's there in it. Where is the water or wastewater treatment plant? If it's rural one, in the countryside, rural one, that means you have open space, right? You have land, so you can use just air drying. And you can use composting to treat that sludge remaining, all right? Use it for agricultural purposes there. That's for good for rural areas. Air drying, just keep it to dry in the air. So water gonna evaporate and the remaining is the solid sludge, right? Much of that solid sludge is really rich in nutrients. So it can be used as composting, all right? If the water and wastewater treatment plant is inside cities, you cannot maybe do that. You cannot afford that. Especially you have here odor, right? Smell. So there you have different mechanisms for dewatering, conditioning, right? Other things as well. All right. So let's look at the process here. Then we'll see some video here. Actually, the video is long. Quickly, these are the steps. All right. Thickening, conditioning, dewatering, reduction. All right. Reduction means burn it, incineration. This is why you see ash here. Landfill. All right. Dewatering is the main process here. You get rid of water. Before that, you need to do some stuff here, thickening and conditioning. Thickening, when you have solids are still there, you know, suspended or whatever, you need them to either settle, so it becomes one kind of blanket together. This is what we call thickening. Or sometimes they push them up using air. They call it flotation, all right? So they come together and form one kind of blanket, so they collect it together, right? Conditioning means add some kind of stuff to it, such as lime or alum, to make it ready for the watering process. Okay. Stabilization, here is where you need to kill the pathogens. All right. You need to kill the pathogens. Some guys don't take everything to the sanitary fill. They use it for irrigation purposes. Or you take everything down the road to aerobic digesters, and from there you produce methane gas from it. Okay, so let's look at these quickly. Thickening, all right. Okay, thickening, make it thick. In other words, bring them together, bring the solids together, all right? Different ways, gravity thickening. If needed, you can add flocculants to them, such as alum, let them flocculate and bring together, either using these tanks, exactly as you did with flocculation. You need to stir them as well, or flotation. Sometimes they use, okay, what's happening here? Oops, oops, oops. That's the picture. Somewhere else. Sorry. All right. So either flotation or gravity. All right. If it's a primary sludge, gravity. If secondary flotation, they use different technologies. This is how they use flotation. All right. You don't need to go in details on this. Just they apply some air from beneath. All right. So they're going to form that thick blanket. All right. There is a conveyor it's gonna carry it and take it somewhere else. Here is the technology for that. Conditioning, adding chemicals to make it ready for the dewatering process, different kind of treatment here. Heat treatment as well can be used. All right. Dewatering, this is the most important process. you get rid of water, right? You get water. Sand drying beds. All this and still in use. Cheapest, very simple, low maintenance, very effective. But you cannot do this during winter time. You don't need rain, right? Here, how they do that. See the beds here, how they dry them. Looks like snowing here on these beds. I'm not sure what happens with this snow down the road. They keep them under the sun also. If this is not effective, use mechanical dewatering, all right? Squeezing, see, squeezing. You bring them wet inside this machine, you rotate them, and you squeeze out the water, all right? Or centrifugal, right? You bring it in a device and it's gonna rotate, right? And while rotating, water goes radially out and the solid stays in, all right? It's the same as the dryer next to your washing machine, right? Similar to that. Or filter belts, all right? Filter belts. This is kind of shear, all right? It's gonna, two drums gonna rotate and the sludge gonna come between them and it's gonna squeeze it out. All right, like here, what you see in this picture. See these belts here? This is solid, dry, no water in it. Okay. Reduction, as I said, this is incineration mainly. You burn it, right? Burn it. Or oxidation. Stabilization, aerobic digesters and anaerobic digesters as well. Alkaline also by adding lime, right? This is to deal with the pH, all right, to change the pH. Now, aerobic digesters, this is exactly as what you have in the aeration tank with the bacteria, with the microorganisms, right? Aerobic. The whole idea here is you have now in this sludge too much bacteria, microorganisms. You don't need them. So what to do with them, all right? Keep them eating until they eat everything. After that, they're gonna die, all right? This is the whole idea about aerobic digestion, right? The other process here, see what they do here? Aerobic digester. The sludge here has too much of microorganisms, all right? If you don't supply them with food in a form of BOD, if you don't do that, eventually they're gonna consume all the BOD here and they're gonna die. So this is how you get rid from these guys, all right? However, there is also other types of bacteria here, all right? In the anaerobic digester, this is very important and this is very good to do. You can produce methane gas from there. 3 steps, all right? 3 steps. The anaerobic organism is gonna reduce the fat, proteins, whatever's left there, sugars, all right, all these. And they're gonna convert them through fermentation to alcohol or similar material, all right, through fermentation. Then after that, from them to methane gas. And methane gas can be used as a source of energy, right? Through the anaerobic digesters. We are not going to discuss this, but just to know, I have a video actually how they do that. Good. Composting, you can take it also to the land for the land application for soils, agricultural purposes, or if you don't like that, you can take it to the landfill, but be careful with the regulations here before doing that. Okay. Time is it? Let's look at this video if you don't have questions. What is it? Please let me know when you see the video from your side.
See it.
Okay, let's see here how they're gonna. I think this is in one of the universities. They do anaerobic digester there. Michigan State University.
The South Campus Anaerobic Digester at Michigan State University aims to reduce odor and emissions from manure, food waste, and biosolids, create a closed cycle for recycling organic material, and generate renewable energy. The digester will use a mix of dairy manure, dining hall food waste, biosolids, which are nutrient-rich organic materials, and other organic material from campus and the greater Lansing area. Once delivered, the food waste and biosolids will be heated at 160 degrees Fahrenheit for 1 hour to eliminate any potential pathogens. The material will then be mixed with manure from the MSU Dairy Teaching and Research Center and pumped into the digester. The anaerobic digester is a sealed, airtight tank which can hold 300,000 gallons. Organic material will be heated to 100 degrees Fahrenheit and will remain in the digester for 20 to 30 days. Inside the tank, mixers in the digester evenly distribute microorganisms. These microorganisms break down the mixture, producing biogas and nutrient-rich digestate. Biogas, which is roughly 60% methane, is a form of renewable energy which will be used to generate electricity. The system will generate enough electricity to offset the MSU Dairy Teaching and Research Center, around 300 kilowatts per hour, with enough left over to help power MSU. The capturing and use of biogas will generate energy, shrink the carbon footprint of campus, and improve sustainability. What's left from the process is digestate, the nutrient-rich mixture that will be held in the final storage tank until it can be utilized. Mixers in the storage tank will minimize settling for the potential 2.7 million gallons of digestate. Any unused biogas can also be stored in the sealed headspace. The nutrient-rich digestate will be used to fertilize croplands or other biological treatment processes to fuel research opportunities. By utilizing anaerobic digestion technology, the organic materials from MSU will become resources. Renewable energy is created while odors are reduced and emissions are eliminated. This project is one example of how Michigan State University is actively working to improve sustainability.
Make sense? Same idea, but here small scale. In your wastewater treatment plant, it's larger scale. You know, you produce both energy and the digestate. You can take it and apply it for irrigation, agricultural purposes, all right, as compost, fertilizer, in other words, natural, no chemicals, organic, sustainable. Everything should be recycled. That's it. Recycle, reuse, and reduce. Good.
Maybe one day we'll be able to eat it too, Dr. McDaddy.
We eat it.
I'm just kidding.
Well, you never know. Maybe next century we're gonna do something with it. Keep recycling, and we're gonna eat it. You're right. Kind of chocolate, maybe something. Yeah, you never know. Okay, let me show you how in one of the countries they do dewatering. All right, dewatering is important also. It's long video. We are not going to watch all of it, but to get the idea. Sorry, I didn't share that. Okay, it's shared. All right, please tell me when it's there.
We can see it.
All right.
Over the past decade, tanners in many countries of Southeast Asia have installed individual or joint effluent treatment plants to treat the effluent generated in the leather-making process. India alone has 16 common effluent treatment systems and over 180 individual effluent treatment plants for tannery effluent. Large common treatment plants have also been set up near Shanghai in China and at Samut Prakarn in Thailand. Another is under construction in Kasur near Lahore, Pakistan, and yet another is to be set up at Bata Atta in Sri Lanka. Effluent treatment involves removing the suspended solids and heavy metals, usually by means of chemical precipitation. This physico-chemical treatment results in the production of sludge. Approximately 3.5 to 4 kilograms of sludge, dry matter, is produced from every cubic meter of effluent treated. In many countries where sunlight and land are amply available, sludge from smaller plants is dewatered in sludge drying beds. The most common mechanical sludge dewatering equipment includes a centrifuge, a chamber filter press, and a belt filter press. In many countries, the sludge emanating from tannery effluent treatment plants is categorized as hazardous waste since it contains chromium, albeit in its rather benign trivalent form. However, in the United States and many European countries, tannery sludge has been deleted from the list of hazardous wastes. More recently, effective and efficient sludge management has taken on great significance in many developing countries in Southeast Asia. This is the outcome of the strict enforcement of stringent laws governing the disposal of hazardous waste. Under its regional program for Southeast Asia, the United Nations Industrial Development Organization, UNIDO, has launched a number of initiatives designed to help the industry deal with sludge management effectively. Sludge management options fall into three broad functional areas: reducing the volume of sludge generated, converting it into byproducts, and disposing it off safely in a properly developed landfill. Let us take a look at the technological choices under each of these options. Under reduction of volume, the choices demonstrated are partial substitution of chemicals such as lime and alum by polyelectrolyte and anaerobic digestion of sludge. Using polyelectrolytes to partially substitute conventional chemicals such as lime and aluminium chloride helps reducing the sludge volume by as much as 15%. Sludge volume can also be reduced by digesting the sludge anaerobically. This process entails a degradation of organic matter by microorganisms. UNIDO has installed a pilot and demonstration anaerobic digestion unit at the CETP in Vaniyambadi, Tamil Nadu, India. It has a capacity of 5 cubic meters per day, and its primary objective is to show how sludge volume can be reduced. Sludge is taken from the soak and pickle streams for digestion, given its high organic content. The sludge is first settled in a settling tank and then fed into an anaerobic digester that mineralizes the sludge, thus reducing the total sludge volume. Digestion also improves the dewaterability of sludge. Though it is too early to draw any conclusions as to its viability, results to date indicate that depending on the organic matter content in the sludge, anaerobic digestion can reduce sludge volume by 30 to 50%. For conversion of sludge into byproducts, the choices demonstrated are biomethanation and generation of electricity, composting with other organic wastes, and solidification and immobilization of heavy metals. Often, the organic content in primary sludge is not high. In instances where it is low, combining sludge with other organic-rich waste materials can facilitate digestion. An ideal solution is to combine it with fleshings, another organic waste from tanneries that often poses a serious disposal problem. Wet fleshings can be minced and mixed with wet sludge. In addition to helping reduce sludge volume, such anaerobic digestion process also generates biogas, which can be used to generate energy. The sludge from the digester is subsequently dried and disposed of. Set up by the Ministry of Non-Conventional Energy Sources of the Government of India, the Central Leather Research Institute of India, and the UNIDO Regional Program, the pilot and demonstration unit at the CETP in Melvisharam is currently in the process of being stabilized. Its performance will be monitored over the next year. For composting purposes, tannery sludge has to be combined with admixtures with a high carbon content. UNIDO has established a pilot and demonstration unit in Melvisharam where the composting of sludge emanating from the CETP has been attempted. Composting trials were conducted using different combinations. Sludge was mixed with admixtures such as vegetable market waste, green biomass, tannery fleshings, hay, cow dung, etc. It has been proven that effective composting of sludge with these amendments is feasible. 50% of the admixture can be sludge and the other 50% a combination of other wastes. With appropriate amendments, the temperature of the heap rises to over 65 degrees Celsius within the first week. It takes about 55 to 70 days for the compost to stabilize, and the yield is between 80 and 85%. The coarse material is screened out for reuse in the next round of composting. The fine compost is packed for marketing. It has been found that in terms of NPK value, the quality of compost is similar to those of urban compost and farmyard manure. Compost application.
Are you familiar with the NPK?
Yeah, nitrogen, phosphorus, and potassium.
Yes, thank you. You always read that when you buy them from Lowe's or Home Depot fertilizer, the NPK. Yep, that's it. All right, guys, I think that's it about it. Just give you an idea about how they do stuff, different options, as they said in the video. So it depends what you have, and based on that, you choose what to do. Okay, I think that's gonna be enough for today. Okay, if you don't have questions, then we can stop here. And next time we start stormwater. All right?
Sounds good.
No
Thank you.
questions?
Thank you.
Thank you. Enjoy the rest of your day, guys.
You too.
Too. Bye-bye.
Bye.